Acceleration in two dimensions is one of the more difficult concepts you'll go over in this class, and one of the easiest ways to learn it is just by doing a bunch of examples. So this video we're going to go over a number of different examples, problems you might be expected to solve. So we'll start with a fairly easy problem. Imagine that a baseball is thrown, and we'll give it certain x and y component velocities. In the x direction it's going 15 meters per second, and in the y direction it's going 10 meters per second. And we'll go through and calculate how far does it fly and how long does it take to get there. So the first step is almost always write out all of the variables. So we'll say our x initial equals 0, our x final equals something, we don't know what it is, y initial equals 0, y final also happens to equal 0. This ends when it falls back to ground level, which is at 0. The velocity sub y, that's the original velocity in the y direction, is 10. Velocity sub x, the original velocity in the x direction, is 15. The time is something we don't know. And the acceleration, we'll say it's negative 10 meters per second squared for now. So now let's go through and see what we can calculate. We either need to calculate either position or time. And since our position is going to depend on our time, let's start with time. So we need an equation that uses time and only other variables that we have answers for. So a good one is change in velocity equals acceleration times time. Acceleration is a constant, and between the ground and the top, the change in velocity is the final velocity, 0, minus the original velocity, 10, equals negative 10 times time. So negative 10 equals negative 10 time. Time equals 1 second. And before we get too far into this, let's think for a second. 1 second is the time it takes to change 10 meters per second. That's going from the bottom to the top. But it also has to fall from the top back down to the bottom, which is once again a change of 10 meters per second. So that's another second. So our total time is now not 1, but 2 seconds. So now that we know time, now we're ready to move on to position. How far does it fly? And once again, we can use a simple equation. We can say that x equals the velocity in the x direction times time. Velocity in the x direction equals 15. Time equals 2. So x final, x at the end, is 30 meters. 15 times 2. So that's easy enough. So now we have answers for both the position and for the time. And the same technique can be used in almost every single problem. Figure out what you know, figure out what you need to know, and find equations that incorporate the things you know and solve for the things you don't. So let's go on to a different example. In this example, an astronaut travels to a distant planet and wants to determine what gravity is. So he takes some sort of rock and throws it up in the air. The astronaut stands on the surface of the world, and he throws a rock upwards, and he knows he's throwing it at 20 meters per second, and he knows it goes up a grand total of 30 meters. So how far up in the air does it go? So we go back to write out our equations. We know our velocity initial equals 20 meters per second. At its peak, velocity final equals 0, because that's what it means to be at the peak. If it wasn't 0, it'd still be going up or coming down, it wouldn't be at the peak. The change in x is unknown. We don't know how much x changes. Or sorry, we do actually know how much x changes. X changes by 30 meters. What we don't know is we don't know what acceleration is. That's an unknown. So now we need some piece of data that uses all four of these and can solve for acceleration. And here we'll use v squared equals vo squared plus 2ax, because it incorporates the three things we know, x, v naught, and v final. And v naught is the same as v initial, just the original velocity or the initial velocity. It means the same thing. So we plug into this, the final is 0 equals 40 meters squared per second squared plus twice acceleration times change in x, which is 60 meters times acceleration. Solving through, we subtract 40 from both sides and divide by 60. You end up with negative 40 over 60 equals acceleration. So the acceleration is a scant 2/3 meters per second squared. And this result implies that gravity is way less than it is on Earth. It's less than 1/10 of Earth's gravity. And that makes sense because he was able to throw it very, very high in the air with a fairly minimal original velocity. So let's do one final example problem. For this problem, imagine that a pitcher throws a ball going forward at 30 meters per second. And we know that it travels a good distance of 150 meters. Figure out how hard he threw it in the air and what its max height was. So once again, we write out all of our possible variables. So here are all of our different variables, and we know some of them, we don't know others. So the first thing to do is we should either try to figure out the velocity or the time. And the velocity is going to depend on the time. So let's start with the time. And we can use the same equation, x equals vt, in this case v sub x. So x, which is 150, equals 30 times time. Dividing both sides by 30, we get 5 equals time. So the time is 5 seconds. So now that we know the time, now what we need to know is what was the y velocity. And we can use the at squared formula. So y equals yo plus vyt plus 1/2 at squared. Y equals 0 equals yo also equals 0. And at this point, it's tempting to think that we've made a mistake. 0 equals 0 doesn't make a lot of sense. But let's continue through to the end. Plus v sub y, the y velocity, times 5, plus 1/2 at squared. 1/2 of a is negative 5, and t squared is 5 squared, or 25. So as a result, we can say 5 v sub y minus 125 equals 0. So v sub y equals 125 over 5, or 25 meters per second. So that's the velocity y. So now we've solved all the parts of this equation. We found the upwards velocity, how long it took to fly. And we just did this the same way we've been doing before. Write out all the equations, figure out the ones that we don't know, and find equations that can help us solve for ones we don't know. And one of the really important tricks here is you have to find equations that we're only missing one piece of information. If we're missing multiple pieces of information, it's going to be too tricky because we're not going to be able to solve it because the two pieces will depend on each other. So it's always very important to find some equation that only has one missing part and then plug and chug from there.